So you get, the accounts now are not paying hardly anything. But let's say you're getting, on your account, you're getting 2% interest. That interest is being compounded, I guarantee it, some way, shape, or form. Probably monthly. When your interest is compounded, we're gonna use this formula. Now, if we just used this one, let's say you put $100 in at 2% interest, would you agree that that would be the setup for that? 2% growth? But that is 2% per year. So that means that if you deposited that money today, 1 year later, the bank would give you 2% on that money. And then the next year, they would give you 2%. That's not the way your bank does it. Your bank compounds it monthly, which means at the end of every month, they give you a portion of your interest, the interest, a 12th of your interest they give to you. And then next month, they give you another 12th and another 12th. Now, what's the benefit of that? What's the advantage of that? Okay, well, let's go back to the front side of the page. Let's go back to the front side of the page. And let's go down to question number 5. Actually, no, let's go down to question 3. Let's just look at 3B. Let's consider what happens when we get interest paid out multiple times in the year in smaller increments. We'll explore interest that is earned quarterly. All right, quarterly. That means 4 times a year. So this imaginary bank account that you have opened pays you 100% interest. So if you deposited $1,000 at the end of the year, you'd have $2,000. Would you agree with me on that? Okay. This is imaginary, of course. But that's what would happen if they paid you annual interest, if they just paid it at the end of the year. Now we're going to look at it if we do it quarterly, every 3 months, quarterly. So I'm looking at question 3B. All right? The amount invested is $1,000. The percent interest earned each quarter. Well, since it's quarterly, we're going to earn 25% each quarter. So how much would be in the account at the end of the first quarter? Well, wouldn't it be your $1,000 times 1.25? You're getting 25% interest. So what is that? $1,250? So now your bank account at the end of 3 months has $1,250 in it. All right? Now, what about the second quarter? Well, now wait a second. This is how much is in there the first quarter. So now, aren't we taking $1,250 and adding on 25% of that? So what's that? $1,562.50. All right, and then the end of the third quarter. Now you're taking your $1,562.50 and multiplying it by adding on another 25%. So now it's $1,953, basically 13. And we're gonna do it one more time because there's 4 quarters. So here's the first quarter, second quarter, third quarter. So now I'm gonna take that guy and times him by 1.25. And it's 2,441.41. So what happened, guys? What's the benefit of compounding interest? What's the benefit of paying that 100% interest in 4 increments instead of all in one lump sum at the end? What happened? You get more money. How come? Why? When the bank paid you your original $250 at the end of the first quarter, now this is what's in your account, and now they're gonna pay you interest on that amount. So they're not just paying you interest on the original $1,000, now they're paying you interest on top of the interest that they already paid, and that keeps compounding. What do you think would happen? This was quarterly. What do you think would happen if we did it monthly?
Be higher.
It'd be higher, because monthly would be 12 times a year, and that means your interest is building on itself more often. This is the formula that evaluates the amount of money in an account in compound interest. A is the ending amount, P is the beginning amount, that's a 1, R is your interest rate, N appears twice in the formula, and that is the number of times per year that your money is growing. So in the example we just did, I didn't use the formula, but if I were going to use the formula, my N would be 4 quarterly, monthly N would be 12, daily 365, and so on, and T is the number of years. So next time I do this problem, I won't go through and do each individual calculation. I'll just go straight to my formula, and it will give me the amount of money that I end with. Okay? Now, what would be, do you think, the best possible scenario then? You said monthly was better than quarterly. Daily would be better than monthly, right? What do you think would be the best possible scenario? It's called compounded continuously. So that means whatever it is growing every single second of every single day, all the time. Populations grow this way. You don't just magically go from 100 people to 200 people. They grow incrementally on a continuum. That's what this formula does. Again, this is the ending, this is the beginning, this is the rate put in decimal form, so 3% would be 0.03, and T, that's your time, and that's kind of dependent on the scenario. This formula, T, is always in years. This formula, because it applies to nature, it can be minutes, it can be decades, it can be whatever, and your rate will be proportionate to that. And then that's Euler's constant E. Okay? All right, now let's go back over to the back side. And let's see if we can work through some of these problems. Okay, so here we go. Estimates of the numbers in millions of U.S. households with digital televisions is given by this. Where T represents the years after 2000. Okay, and this is the number of T's. Is the number of households with digital TVs increasing or decreasing between 2003 and 2007? Justify your answer. Julia?
It'd be increasing because the number that you're multiplying by is over 1.
Exactly. the base of the exponential here. This is a times b to the x. Your base here, this guy right here, is bigger than 1. So that's going to be growth all the time. It doesn't mean 2003 to 2007, okay, fine, but it's all the time this is growing. What does the 30.92 represent? That's how many TVs there were in 2000, the beginning of the count, 2000, and that's million, 30.92 million televisions. What does this represent? So a 1.2% per year increase, 1.2%. Use the model to estimate the number of U.S. households with digital TVs in 2015. Well, that's easy. What would you do? Plug in 15, exactly. So we would have, do I hear the heat coming on? That thing will start up. 36.978 million TVs. Actually, not TVs, but households. On the day of a child's birth, a deposit of $25,000 in a trust fund that pays 8.75% interest. Determine the balance in this account on the child's 25th birthday if interest is compounded weekly, monthly, and continuously. Okay, weekly, monthly, and continuously. So we're starting with $25,000. Our interest rate is 0.0875. Let's do weekly first. If we do weekly, what's our N? 52. And we're doing it for how many years till he's 25? Okay, so let's just type that in, make sure everybody can type that in. This was weekly. Okay, tell me what you got for weekly. You guys are not helping me out much today. Let's try to wake up, participate a little bit. What? Lot, $222,413.32. Not bad. Now they ask us to do it monthly. So monthly, everything's gonna be the same except what you're in now for doing monthly. Well, so go ahead and try that one, see what that comes out to be. Do you think this is gonna be more or less than 222,000? Be less, good job. Because we're compounding fewer times. still a big number. What did you get for this one?
221, 6.10 cents.
$229,061.10. And then it says continuously. So that's your other formula. That's your formula with E in it. It's your growth formula, or your natural growth formula. This one should be the highest of all. Let's see if it is. Everybody good?
What would R be?
0.0875. Where's your interest rate? You're called your growth constant, but the money problem, that's the interest rate. Julia?
For the last, for the continuously equation, why does the R have to be 1.0875 since it's increasing?
Okay, so let's talk about that. It isn't 1.0875 in any of these problems. The interest rate goes in as itself, whatever it is. Remember that this, right here, this is your base. That's your exponent. This is 2.7. It's already way bigger than 1. Okay? So there's no rules about the exponent. The rule is about the size of the base if you're talking about growth, okay? Unless, of course, your exponent is negative. That's it. But no, any size positive exponent on this base is going to grow. So the bigger that number is, the more it's going to grow, but it's going to grow, period, as long as it's positive. All right, number 3, the number of bacteria increases according to a continuous exponential growth model. Here it is, that's your continuous exponential growth model at a rate of 8.1% per hour. There are 1,800 to start with. Interest rate is 0.081. Write an equation, right here it is, that gives the number of bacteria. You might want to make it a function, so the amount at time t is given by this. Find the number of bacteria after 6 hours, that's easy. Won't we just plug in 6? Did you get about 29, 26 bacteria? All right, let's look at the next page. This drug has a half-life of 3 hours. That word's familiar to you. You've studied half-life chemistry. This means that every 3 hours, your body will eliminate a half of the current amount. In a 30 milliliter dosage of Dayquil, there are 20 milligrams of this drug. After 3 hours, 10 milligrams would still be in your system. That makes sense to you, right? So we're starting with 20 milligrams because we've taken a dose. And then after 3 hours, we have 10. What happens after 6 hours? We have 5. And what happens after 9 hours? 2.5. Easy, easy, easy. How many milligrams of the drug will be in your system after 10 hours? Okay. How are we going to do that? Because these were easy because they were increments of the half-life itself every 3 hours. How are we going to handle how many milligrams of the drug will be there after 10 hours? We're starting with 20, and we're timesing by a half, right? Basically. But we multiply by a half every 3 hours. What do you think? Captain?
Should multiply by 2/3.
Tell me how you got 2/3.
Because if you have 3 hours. Because you only,
We're doing 10 hours.
yeah. So when you multiply, if you have 2.59 hours, you multiply by 2/3. Because you're eliminating 1 out of 3 hours.
Okay, so 1 out of 3 hours. I think that's the key. So when we multiply this by 1/2, that was 1 half-life period, right? A whole half-life period. This was 2 whole periods. This was 3 whole periods. So what's 10 hours? 3 1/3, so 10/3 basically. Yeah, so you're on the right track. Yeah, you were thinking about the right things. But that's it, because every 3 hours is a whole half getting taken out. So this is 3 wholes and an additional third, an additional hour. All right, so I don't know what that is, but that would be it. What percent of the drug remains in your body after 1 hour? Now remember, when we times by a half, that told us how much was left, right? So how are we going to do 1 hour? It's half-life, so you gotta have a half in there. But how are we going to do 1 hour? Thank you, Quinn, appreciate that very much. Now, this is how much is actually there. So 20 times 0.5 to the 1/3. So it's about 15.874 milligrams, or whatever my unit is here. How do I find a percentage though? What would I need to do to find what percent remains? Put over 20? Exactly. So it's about 79.37%. Which, by the way, you guys, if you type in 1/2 raised to the 1/3 power, just 1/2 to the 1/3, that's the decimal that you get. So if that much remains, what percent has been eliminated? This remains, so eliminated has been 20.63% if I subtracted right. Write an alternate formula for this, and this is the formula we've been using. Y equals 20 times 1/2 to the t. you're using that kind of a formula. Write an alternative one that can be used to model the amount in your system after after T hours. Clearly explain what your A and B values represent in this context. So what do you think? Right this way. Okay, so let's wake up, think for a second. I need a new formula. This reflects this half-life thing. I went ahead and divided by 3 because if T is gonna be in hours, I have to divide by 3 because every 3 hours is when I get halved. Does that make sense? That's the formula we kind of been using. All right, now we're gonna come up with a new formula. Using not the half-life idea, just a regular exponential. I think I'll start with 20. Does that make sense, everybody? That's how much the drugs in my system to start with. Assuming you wrote down, listen to what we just said. A moment ago, didn't we find out the percent that was left in my blood after 1 hour? What was that number? I erased it. 0.7. What was it? 7? No, that's how much was eliminated. Oh my God, nobody even wrote it down. Oh my God.
No, it's 37.
Thank you.
79.
Thank you. 0.7937. Okay, that's the alternative formula, guys. The original half-life formula that we came up with, this was like 1/3 T. So we figured out that this guy right here was the percent that we were increasing every hour, the growth that we were actually decreasing every hour. So instead of using 1/2 to the 1/3, we'll just figure out what that decimal is, and that becomes our growth constant. We talked about this last week. The benefit of doing that is now you can look at your equation and tell that every hour I am losing about 20% of this stuff. Because this is what I'm keeping right here. That's the percentage that's staying. So I can look at this and say, oh gosh, I'm losing about 20% every hour. All right. Would you right now with your partner try the back side of this paper? These are exactly like, well, number 2 is a little trickier, but number 1 is just like what we've been working on. Spend a couple minutes while I'm handing back papers and figure out, if you can, the answers to 1 and 2 on the back side. Yes?
I may go to the bathroom. I'll run. I'll sprint.
Yes, you can hurry up. Maybe that'll wake you up. I don't know. Remember that your papers are due on Friday.
Yeah. I was just gonna say one. I was just doing that to remember. And then that's what I was thinking. 3.75.
Every 5
Yeah. Well, I was not shocked.
You were shocked. It's all right.
Equations.
Well, it says every 5 days, so it's like compound 17 days. Right? Well, what if we do this one? But it's like negative interest. Does that make sense? Can we do that?
And then it's okay by
Well, you don't have to necessarily change that. Yeah.
British.
So divided by 7.
I don't know what I was doing.
That did not work.
No. Okay.
Yeah. What if we try to find how much it increases in one day?
Okay, let's start talking about these a little bit so I can get your test papers back to you. I kind of drew a little picture to get started here. It decays by 25% every 5 days. So after 10 days, I've got 45 left. So I just said, and you might have thought about this differently, I just said whatever I started with, if I multiply that by 0.75 twice, I should end up with 45. Does that make sense? Why am I multiplying by 0.75?
Because it's a decay of.
It's decaying 25%, so my base is what I'm multiplying by is 75% of what I started with. So I got 80. Did you get 80 to start with?
Yep.
Okay, good. Now, that's a good number to have, because now we're going to set up a formula, and we need to know what we're starting with. We're starting with 80. And we're multiplying by 0.75. Now, this is in days, so don't just put a T up here, because that isn't what's happening. What do we have to put up there?
T over 5.
T over 5. Because every 5 days, we end up with 75%. So if T is 5, 5 over 5 would be 175%, right? And then 10 over 5 would be 275%, and so on. find E of 7 over E of 6. Okay, so I can do that. E of 7 over E of 6. So type it in there on my formula, or on my calculator. Did you already do this? I can save time if you've already done it. I got 0.944. Yeah, is that what you got? Can somebody double check that before I go on? I wanna make sure I got the decimal right. Did you get that?
Yeah.
Okay, what does that mean? What does that decimal mean? We took the number, the amount of the stuff we had after 7 hours and divided it by the amount we had after 6 hours, and we got this. What does that stand for? Every hour. So this represents the hourly change. Wasn't this the change for 1 hour here? So that means, like he said, every hour we are losing about 5%. Take your calculators real quick. Type 0.75 to the 1/5. 0.75 to the 1/5. Don't you get 944? So another way, this is 1/15. So this right here represents the hourly change. That is the per hour change. The 0.75 is the per 5 hour change. This is the hourly change. All right, on the Great British Baking Show, a contestant takes cake out of 100, okay? So we have, this is a repeat of what we talked about last week. Let's see if we remember. We have to find the values of A and B. So what do you think? Well, are there any ordered pairs in the problem at all? 10 minutes. So if T is minutes and C is temperature, I have the ordered pair 10, 150. With two variables here, I really need another ordered pair. Do I have another ordered pair in the problem? 0, 180. Beautiful. So now what can I do to start figuring out what my variables are? Plug them in. So 180, I'll use this one first. 180 equals A times B to the 0 plus 3. Is that right? So 100, what's B to the 0? So 180 equals A plus 3, so it looks like A is 177. Yeah, wow, that's nice. So then I'll do this one. So 150 equals 177. already know A, might as well use it, 177. B to the 10th plus 3. So 147 equals 177 b to the 10th. So 147 over 177 equals b to the 10th. So what do I need to do now? Either take the 10th root or raise to the 1/10 power, whatever's easiest for you to do on your calculator. And I got 0.982. So my equation is 177.982 to the teeth plus 3. And that will tell me the temperature of my goods when I take them out of the oven. And set them down for a while. All right,